it's Coach Stricker, and I'm here to talk to you about electron configuration. Yesterday, we went over the basic of what electron configuration looks like. So if you have oxygen, oxygen's electron configuration is 2p4 for its final electron configuration. That 2 stands for the principal energy level, the p stands for the sublevel, and the 4, the exponent 4, stands for the number of electrons. And so what you're going to see today is that is the final electron configuration, but we're going to go over today how to build electron configurations and show every electron and account for every one. But there's one huge rule that you have to start off with, and that is the Aufbau Principle. And the Aufbau Principle says that you must fill up electrons in order of the lowest energy levels first. All right, so that's why you always start off with 1s. So the order is going to be 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, up to 7s. And that is from the lowest energy level to the highest. So what does that mean? Okay, that means when you come over here, you're accounting for every electron. So we start off with the lowest energy level, and it's in order. So energy level 1 has 1s1 and 1s2. Remember, helium would go over here. So that would be 1s1 and 1s2. That is in the first energy level. That is the lowest energy level, and that's where the first 2 electrons go. The next 2 electrons, 3 and 4, go into s. We said that the s sublevel has 1 orbital, and you can fit a maximum of 2 electrons. Well, if both of them are filled up, then you're using the 2s1 and the 2s2. Then, if you come over here, and we're stopping at oxygen, because that's where we were, oxygen ends at 2p4. Well, you've got 2p1, 2p2, 2p3, and 2p4 represented. All right? So, the electron configuration, you're accounting for every electron up into that point. So let's do silicon. Silicon has 14 electrons. How do I know that? Because that's the atomic number. The atomic number stands for the protons and the electrons. And the ending electron configuration for silicon, it's right here, is going to be 3p2. All right, 3p2. So basically, that's where my ending point is. I have to fill up everything up until 3p2. So this is going to be my ending spot. And I have to fill up 1s, 2s, 2p, 3s, and then all the way up to 3p. So 1s, when it's filled, is going to be what? 1s2, because you can fit 2 electrons. 2s filled is going to be 2s2, because you can fit 2 electrons. 2p, p's can fit up to 6, right? Because it's got 3 orbitals, so 2p6, 3s2, and then I stop in 3p at 3p2. How do I write that out? You write it out like this. 1s2, 2s2, 2p6, 3s2, 3p2. Now, you can check yourself by adding up the electrons. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 2 is 14. If you have 14 electrons accounted for, then you did it correctly. All right, now, this is a lot easier, okay, than doing it the long version. The long version would be you have to represent all 14 electrons. So it would be 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, all the way up until you get there. I mean, that's just terrible, right? It's a lot of writing. So rather than doing 1s1 and 1s2, the 1s sublevel is filled. So if I put a 1s2, that accounts for both of these. So I don't have to write both of them, I just write that. The 2s2 accounts for both of those, so it's filled up. The 2p6, I don't have to write 2p1 all the way through 2p6. If I write 2p6, that accounts for all 6 of those. So this is a shorter way of writing it, all right? And it should save you some time, because when you get up to like 38, that's a lot of letters that you're writing. All right, so that is the electron configuration for silicon. All right, now let's do another one. What if we have iron? Iron is Fe. All right, what is the atomic number for iron? It's 26. All right, so that means I have to show 26 electrons. So how do I do that? Well, I've got to fill it up. What's the final electron configuration going to be for iron? It's going to be 3d what? 1, 2, 3, 4, 5, 6. So it's going to end at 3d6. So that tells me that everything up to 3d6 is going to be filled. But you have to start at the lowest energy level first. That's why we always start off with 1s. 1s is filled with 2, then we go to 2s. 2s is filled with 2, then I go to 2p. 2p is filled with 6, then I go to 3s. 3s is filled with 2, then I go to 3p. 3p is filled with 6, then I go to 4s, filled with 2, then I go to 3d, and I only have 6. That's not all the way filled up, because if it was filled up, I'd have 10, and I stop at 6, because that's where I'm at, in here. All right, so then I add them up. 2 plus 2 is 4, plus 6 is 10, 12, 18, 20, 26. And that is the atomic number for iron. So that would be correct. So that's how you do electron configurations. You have to fill up from the lowest energy level to the highest, and you have to do it in order. All right? Now, that is called the Aufbau Principle. All right, when you're filling it up from lowest to highest of energy levels. All right, there's another thing called the orbital diagrams that we're going to be talking about. Now, orbital diagrams, not only are you showing the electron configuration, now you're showing electrons with arrows, and you're showing the orbits. Well, we talked yesterday about the orbitals, right? So S has 1 orbital, okay? P's have 3 orbitals. D's sublevel has 5 orbitals, and the F block can have 7 orbitals. All right? And so you're going to represent those electrons that are in that with arrows. Like that. Now, the book might have boxes, and you put them in boxes, but I just like to draw the lines because it's less work. All right? So, let's do the orbital diagram. Actually, I forgot to say, the Pauli exclusion principle is the next rule. There's 3 rules. Aufbau rule, Aufbau principle says you go from lowest energy level to highest. You have to. Pauli's exclusion principle says that only 2 electrons are going to fit per orbital, and they must have opposite spins. So, what does that mean? That means that when you're putting them in the orbital, okay, so if I have 1s, 2, I have to put them in with opposite spins like that. Up arrow, down arrow. If I put up arrow, that is wrong. If I put down arrow, that is wrong. All right, you have to put up arrow and then a down arrow to fill up because it has to have an opposite spin. All right, now the third rule is Hund's rule. And Hund's rule says that you can only have 1 electron per orbital in each sublevel until all the orbitals have 1. Okay, we call that the school bus rule. So what does that mean? Well, if Josh Bartolacci is getting on the school bus, it's the first day of school. He rides a little bus to school, so there's 3 seats. He gets on and he's going to sit in that first seat, okay, hanging out, right? Elijah, we're going to say he gets on, he doesn't know anybody. It's the first day of school, okay? So when he gets on that school bus, he's not going to double up with some dude in the first seat, right? He's going to get his own seat. All right? Then Devin gets on the bus. First day of school. He just moved here, we'll say from California. Doesn't know anybody. He's not going to sit next to someone. He's going to go to his own seat. Now that everybody has their own seat, all right? Jose gets on the bus. Okay, he's going to have to double up. All right? So basically what you're saying is everybody's going to get their own seat until everyone has one, and then you double up. It's the same thing with electrons. When you get to like a 2p4 and you have to show the electrons in the orbitals, you have to put 1 electron in each open orbital before you can double up. So what you could not do if you had a 2p4 is you could not do this and double up like that and leave an orbital open. All right? So you can't leave an orbital open. You have to put one in each one. So we'll say I had a 2p3. You have to put one in each empty orbital, like that. You cannot do it like this, where you would leave one open. Does everybody understand that? Mm-hmm. All right. We call that the school bus rule because you're always going to pick an open seat. So now we're going to do the orbital diagram for, let's do a simple one, for nitrogen. Okay, so nitrogen has 7 electrons and it ends in 2p3. All right, so just like before, you're going to do electron configuration. You start off in 1s2. You draw the orbital, just represent the line. If you want to draw a box, you can draw a box. That makes you feel better. You draw an up arrow and a down arrow. Okay, opposite spins. Then 2s2. All right, up arrow, down arrow, representing 2 electrons. Those arrows represent the electrons. A lot of times you'll see it, and there's actually not even the numbers there. It's just 1s, and then it shows 2 electrons. 2s, and it shows 2 electrons. I don't really care. I'm fine with you putting the 2 there, because that lets me know that you know how many electrons are there anyway. And then you have 2p3. Well, the p's are going to have 3 orbitals every time, and you're going to have 1 in the first, 1 in the second, 1 in the third. Because remember, we don't double up because of Hund's rule before that. So this is the orbital diagram. You can box them in if you want, or just leave them on the blanks if you want. That is the orbital diagram for nitrogen. All right? So what you're going to be doing is you're going to be doing electron configurations and orbital diagrams, and it's very, very important that you remember all 3 rules. Aufbau's rule, you start with the lowest energy level and move to the highest. Pauli's exclusion principle, when you're doing orbital diagrams, when you put the electrons in, they go in, maximum 2 per orbital in opposite spins. In Hund's rule, you must fill 1 in each orbital of that sublevel until you double up the second one.